Hello, everybody, and welcome back. My name is Tabiso Miataza. We continue with mathematics, integral calculus. Right. Let's get to it. Right. Here's a very nice question, which is a very favorite for past examinations. I would like us to tackle it, and I'll explain some concepts for you. Okay. Right, question 14. A curve is such that dy dx is equals to 3 root x minus 9. And the point 4 and 0 lies on the curve. Okay, so we have a curve which has a derivative of 3 root x minus 9. There's a certain curve with a derivative dy dx being equals to 3 root x minus 9. That's the first thing we are given. The second thing we are told is that this curve lies, the point 4 and 0 lies on this curve, or this curve goes through the point 4 and 0. We are then, for question 1, asked to find the curve. Okay, question 1, find this curve. Right, let's do it. So to find this curve, we know that we have been given the derivative, so we have to reverse the derivative. We want to find the function from which this equation was derived from, or that expression on the right hand side was derived from. Right. To do that, we have to reverse it. To reverse differentiation, we have to integrate. We have to do integration. Right, let's do it. So y is equals to, if we integrate this, or rather before we integrate this, let's just do some groundwork here. I'm still going to write it as dy dx. I don't like this square root of x here. I would rather change it, just to make things simpler for us, to be 3x to the power half minus 9. Right, now we can integrate it. So y is equals to, if we take the integral there, y is equals to 3x. Remember, when we integrate, we add 1 to the power. Half plus 1 is 3 over 2. It's 3 over 2 divided by the same power, the new power, divided by 3 over 2. Add 1 to the power, divide by the power, minus, now integrating negative 9 will give us 9x to the power 1 divided by 1. Plus, there is that concept of a constant there, c, that we don't know, which was might have been differentiated, and we found the derivative to be 0, hence it's not there. So we put that c there. Right. So our arbitrary solution for this particular problem then will be right. Let's solve this. 3 over 2 is our denominator. I'm going to tip and times this. No surprises there. So this will be the same as 2 times 3x to the power 3 over 2 divided by 3. So basically what I did was I swapped these around and I multiplied 3 over 1 times 2 over 3. Minus 9x plus c. Right, now we have, simplifying this, cancel those out. Now we have a function y is equals to 2x to the power 3 over 2 minus 9x plus c. Now remember that they didn't ask us for an arbitrary solution. They asked us for a specific solution. They asked us to find a specific curve, that specific curve which we got this from. Now we are going to use the point 4 and 0. This point here lies on the curve. That's a given information. So what we do is we take this ordinate and abscissa and we substitute it into that curve to find the exact value of c, which is the constant, or which is the y-intercept through which the curve cuts, or the intercept through which this graph cuts. So let's do that. So we're substituting our 4 and 0. X is equals to 4, y is equals to 0. Y is equals to 0, and that's equals to 2 times 4 to the power 3 over 2 minus 9 times 4 plus c. And now all we want to do is to work out the value of c there. So x is equals to 4, y is equals to 0. Working it out, therefore C is equals to 20. Now rewriting the whole thing with C into the equation will then give you a specific solution. Therefore, y is equals to the equation itself, which was 2x to the power 3 over 2 minus 9x plus C, which is 20. And there you have it, folks. This is the equation of the curve that was differentiated to get that general solution there. Okay. If not sure about anything, you can try it out. You can try and differentiate this and see if you will get that equation on the other side there. Okay, so this was part 1 of the question. Moving on, part 2 of the question asks us to find the x-coordinate of the stationary points on the curve and determine the nature of the stationary points. Find the x-coordinates and determine the nature of the stationary points. Find the x-coordinate and determine the nature of the stationary point. Find the x-coordinate of the stationary point and determine the nature of the stationary point. Stationary points. Now, for stationary points, we are going to say let the derivative dy dx be equals to 0. Those are static. If you remember from our differentiation and graph sketching, I explained this a lot. What are stationary points and why do we let them be equals to 0? Okay, at the gradient there. So please just revert back, go back to your differential lessons, and you will see that. For now, I'm just going to take it at face value that you remember. For stationary points, I'm going to let dy dx be equals to 0. That's the first thing I'm going to do. So remember that now you don't have to differentiate this. You are given a differential equation already. You are given a derivative equation, 3 root x minus 9. So I'm just going to say, therefore, 3 root x minus 9 is equals to 0. I'm going to solve that equation. Most common thing to do would be to square on both sides of the equation so that you can remove this square here. There's a lot of mistakes that come with it, so you have to be very careful. If you are squaring this as it is, then you have to FOIL. And when you are foiling, you're going to get something like negative 54 square root of x plus 108 or something like that. And some people get really, really scared when they see those big numbers, and you have to factorize it again, which takes you back to this point. So the best thing to do here, take the negative 9 to the right hand side of the equation. You get 3 root x is equals to positive 9. Now square both sides of the equation. Squaring this side, 3 root x to remove this square root here is equals to do the same thing on the right hand side to make sure that the equation remains balanced. Now squaring that, you get 9x is equals to 81, which means x is equals to 81 divided by 9, which will just be 9. Therefore, at this point, this is the x coordinate for the stationary point. This is the x coord for stationary point. The next thing we need to do, guys, is to determine whether this point is a maximum or it's a minimum. Okay? To do that, we take the second derivative. Okay, again, we've covered this when we were graph sketching, when we were doing graph sketching. To do this, we take the second derivative. So we take dx, beg your pardon, dy squared dx, or d2x, dy squared d2x, in meaning, in other words, you take that function there, this dy dx, and you differentiate it. Differentiating this function will give us 3 over 2 x to the power negative 1 over 2. That's d2y dx squared. Okay. Now let this be equals to 0. And then we, oh, sorry, my bad. You don't let it be equals to 0. You don't want to do sign analysis at this point because I'm looking at the marks for this question and it's not really necessary. So basically from here, what you can do is you've got a point x is equals to 9. The nice and easy way to then do this is I know what the x value for the stationary point is 9. So I am going to take this value that I've found, this x value that I've found, and substitute it into my d2y dx squared, and then analyze from there whether my second derivative is positive or the second derivative is negative. If your second derivative is positive, you have a minimum, a local minimum. If your second derivative is negative, you have a maximum turning point. Okay, remember that d2y dx squared just tells you where the graph changes concavity, either from being concave up to concave down or concave down to concave up. Okay, so that's why I suggest that rather than going on further, just use that. Take this x is equals to 9, substitute it into there, analyze your sign, whether it's a positive or negative, and you can conclude from there, and you can get good results from there. Right, substituting in, this is equals to 3 over 2x. I'm going to put 9 in there, and that's negative 1 over 2. Right. Up to you how you want to do this. You can change this to be 3. You can change this to be 3 divided by 2 root 9. That's the same thing. And this obviously will give you square root of 9 is 3 times that. That's going to be, and so that's going to be 1 over 2 basically, which is a positive. Now remember, positive d2y dx squared means that you have therefore a local, it's positive local minimum turning point. Thank you very much, guys. That was your number 14 there. The next lesson I'm going to do number 15, which is a 2009 from a 2009 paper, Cambridge, and I'm going to do number 16, which is from the 2007 Cambridge papers. Join me then. For now, thank you very much and have a good day.